皆さんおはようございます。本日はクロノスのバーチャルオープンハウスにご参加いただきまして誠にありがとうございます。私はクロノスグループの方で日本の代表を務めております梅澤と申します。よろしくお願いいたします。本日なんですけれども、講演者、こちらのスライドで紹介しているメンバーで行わせていただきます。まず最初になんですけど、私の方は紹介してますので、続いてクロノスの代表、プレジデントであるニール・トレベット。ニールは NVIDIA の方に所属しています。で、次のセッションでは 3D コマースワーキンググループの議長を務めているシュレニック・サダルギ。彼はウェイフェアから参加しています。で、次のバルカンのワーキンググループのご紹介に関してなんですけれども、トム・オルソン、アーム社の方から来ています。で、続いて、バルカンの中にあるサブグループのレイトレーシングに関連するワーキンググループの議長を務めている、ダニエル・コフ。彼は NVIDIA の方から来ています。で、最後になんですが、最後です。その次がバルカンの、機械学習のサブグループ、タスクサブグループの議長を務めているピエール・ブディエ。彼も NVIDIA の人間です。で、通常であれば、クロノスのメンバーからの紹介だけで終わるんですけれども、今回は特別にですね、バルカンの、ディープラーニング、マシンラーニング関係の、タスクグループの事例ということで、AX 株式会社様の方からバルカンを使った、SDK の事例の方をご紹介していただきます。で、始める前になんですけれども、ニールの方から詳しい簡単なクロノスの概要の方は説明させていただくんですが、私の方からちょっとだけクロノスの概要についてご紹介します。クロノスはですね、2000年に設立された非営利の団体でして、シリコンとソフトウェアとシリコンチップを結びつける活動をずっとしています。で、内訳なんですけれども、4割程度が北米からの参加、で3割がヨーロッパ、アジアに関しては3割程度で、日本に関して言うと、大体1割強の会員様が参加していただいています。で、クロノスグループなんですけれども、ハードウェア、ソフトウェア、教育機関、さまざまな、会員様にご参加いただいているんですけれども、どんな分野で活動しているかというのを表しているのがこちらのスライドです。まず1つ目が 3D グラフィックスですね。デスクトップ、モバイル、あとウェブでも 3D が使えるようになってきています。で、それらの 3D のグラフィックスを表示するにあたって、3D のアセットに関しても、ファイルフォーマットであったり、その仕組みっていうのを定義しているグループがあります。あとは、2014年、5年ぐらいから非常に活発に動くようになってきた OpenXR、VR、AR の業界ですね。それに関連して、標準規格が必要だということで OpenXR が出来上がっています。で、最後になんですけれども、クロノスというとグラフィックスのイメージが非常に高いと思うんですけれども、グラフィックスだけでなく、並列コンピューター計算、ビジョンであったり、推論であったり、機械学習において使えるような標準規格の方も制定しています。で、これらの4つのグループに合わせて、それらの API の中でですね、特に自動運転であったり、医療であったり、セーフティークリティカルな API というものが必要になっている部分もありまして、それらのセーフティークリティカルなアドバイザーリーフォーラムというのも存在しています。で、クロノスなんですけれども、組織図としてはこんな形になっています。まず一番上に、ボードディレクトリのボードメンバーがありまして、その下に IP 関連に引っかからないような、アドバイザリーパネルであったり、グループの方が存在しています。で、その下にですね、実際のいくつかの、IP によって7つのゾーンに分けて、組織が構成されています。で、クロノスなんですけれども、エクスシステムを作る場合に、6つの市場区分で考えて活動を行っています。1つ目が組み込みの 3D ですね。続いて、組み込みコンピューター計算の分野。続いて、パフォーマンスコンピューターの分野。続いて、普及型の 3D に関連した分野。そして、昨今非常に話題となっている XR 関係の分野。で、あとですね、パフォーマンス 3D ということで、デスクトップ、モバイルにおける 3D 関係の処理に必要な市場ということで分けています。で、このそれぞれの市場に合わせた、プログラムであったり、開発というのを作るためにいろいろと活動を行っています。で、クロノスなんですけれども、そういったさまざまな会社様が一緒に活動していく上で、どうしても避けて取れないのが特許関係の問題です。 この特許関係の問題に関してどういうふうに行っているのかっていう部分に関して簡単に図で示したのがこちらのスライドになります。詳しくは後ほどニールの方からご紹介させていただきますが、一言で言えば、皆さんを IP の部分の問題から守るためのしっかりしたフレームワークの方が存在していますので、その点はご安心くださいという点になります。で、あともう一つなんですけれども、クロノスの検討グループのプロセスという部分についてご紹介します。クロノスの中ではですね、実は新たな標準規格を作る際に、クロノスの中でこういったものはどうだろうっていうような提案をするのではなくて、実際に業界の中でこういったものが必要なんじゃないかっていう皆さんの声から出来上がってきた規格が全てです。で、そういったものを行うにあたって、そのプロセスがどんなふうに行われるのかという部分がこちらのスライドです。実は 3D コマースというのがこのプロセスにのっとって作られた一番新しい企画になっています。で、この部分に関しても詳しくはニールの方からまた後ほどご紹介いたします。それではなんですけれども、早速各ワーキンググループに関係するご紹介について進んでいきたいと思います。まずはじめは、ニール・トレベットより、クロノスの概要、そして OpenCL、続いて gITF についてご紹介いたします。ニールなんですけれども、クロノスグループの代表を務めていると同時に、NVIDIA において Developer X システムのバイスプレジデントのポジションにもついています。で、現在でですね、数十億人の方が利用している OpenGLES の企画の取り組みを始めたり、もしくは WebGL のプロジェクトに関してもニールが最初に温度を取って、で、OpenCL のワーキンググループの設立に関しても議長を務めて、バルカンの API に関しては最初に確立して、設立を支援する活動をずっと続けて、今も続いています。それでは、ニール、クロノスの概要と gLTF と OpenCL の方をご紹介お願いします。
Hi everyone, I am Neil Trevitt. I work on developer ecosystems at NVIDIA and I am president of the Khronos Group. And I'm going to give you a quick introduction to Khronos, including our goals as a standards organization, a summary of our most active open standards, how we are organized, and hopefully convince you to get involved if you are not already a member. Let's start with our basic standardization question. Just what is an open standard? An interoperability standard enables precise communication, such as between a client device communicating to a server or an API that enables a software application to drive a hardware device. The tech industry uses thousands of standards. They are essential to removing industry friction and to grow market opportunities for everyone. The need for interoperability between hardware and software is growing as hardware technology continues to diversify and software seeks to become portable across multiple platforms and generations of silicon. The definition of a truly open standard is that is not controlled by any single company. And that means we need industry cooperation between multiple companies to create and evolve them. The industry uses standard developing organizations, or SDOs, to enable multiple companies to work together to form a consensus on open standards that move the industry forward. They work under well-defined multi-company governance and IP frameworks, and each SDO has their own area of expertise. Khronos is one of these industry standard developing organizations, an open standards consortium. We provide a safe place for the industry to cooperate and create interoperability standards that enable applications to access the power of 3D graphics, virtual and augmented reality, and parallel computation. We are a non-profit organization, and all the standards we create are open and royalty-free for the industry to use. We have been creating standards for 20 years and have almost 160 members that include everyone from the largest companies down to small startups. Any company who wishes to join Khronos is warmly welcomed to participate, to have a voice and a vote in how Khronos standards evolve. Here are the standards currently being most actively developed by Khronos. There are 4 main groups: 3D acceleration APIs, including Vulkan, OpenCL, and the new Inari API for analytic rendering. Initiatives around 3D asset formats, including glTF and 3D commerce. The OpenXR API standard for portable, augmented, and virtual reality. and on the right, a family of APIs and languages for parallel computation, vision acceleration, and inferencing, including OpenCL, SYCL, Spear, and OpenVX. In addition, with the increasing use of open API standards in safety-critical markets, such as autonomous driving and robotics, Khronos has developed safety-critical variants of its OpenGL and Vulkan 3D APIs, designed to reduce the safety certification costs of systems that use them. Together with a safety-critical advisory forum, which is free and open for anyone in the industry to join to help create guidelines on how best to design APIs targeting safety-critical markets. Khronos standards are often used one at a time, but synergies often arise when they are used together in specific market segments. Khronos identifies 6 such segments and pays close attention to creating holistic solutions for these developers. The first of these segments is performance 3D graphics on desktop and mobile devices that have many years used the Khronos OpenGL and OpenGL-ES APIs, and now the industry is moving to the new generation Vulkan with SpearV enabling significant innovation in shading and language kernel compilers. The embedded industry can use the same desktop GPU APIs, but has also created safety-critical versions of both OpenGL and Vulkan to ease system safety certifications. The embedded computation market can use those GPU APIs for GPU acceleration, but it has also evolved general-purpose compute-only APIs such as OpenCL and SYCL, and vision and inferencing acceleration frameworks such as OpenVX. Applications needing access to high-performance compute on desktop and supercomputers may use OpenCL or SYCL, which is often layered over OpenCL, with Inari used to visualize simulation results. Both compute and graphics applications often need access to pervasively available 3D assets held in the glTF file format, with WebGL making 3D rendering available in any browser, with the emerging area of 3D commerce leveraging both of these standards. And finally, augmented and virtual reality applications are a good example of where glTF 3D assets are vital together with Vulkan and WebGL, enabling XR graphics rendering natively or in the web, together with OpenXR, providing portable access to HMD displays and devices. As Khronos works to create these open standards to meet industry needs, it consistently adheres to a number of core principles. Firstly, Khronos membership is open, and any member is welcome to join at any time for a full voice and a vote in how any Khronos standards evolve. Secondly, Khronos works hard to ensure its standards are responsive to real industry needs by enabling proposals for new standard initiatives to come from any company, whether or not they are members, and focusing resources on standards that become widely adopted. Organizationally, Khronos has an effective IP framework that provides strong protections for members' IP, but also enables royalty-free industry standards through members agreeing that they will not assert their patents against conformant implementations of standards that they have helped to create. Khronos invests significantly in conformance tests, as they are vital as the specification itself to define a true standard that can be reliably implemented by multiple adopters. And finally, Khronos is a non-profit organization where all membership and adopters' fees are used to fund Khronos activities for the benefit of the industry. Internally, Khronos creates a working group to manage and evolve each of its standards, and all members are free to join as many working groups as they wish. Many working groups have advisory panels of invited industry experts to provide requirements and feedback on specification drafts. The Khronos board is made up of companies that pay a higher membership fee and are motivated to help set the strategic direction for Khronos, including how Khronos directs its budget. Each working group has a number of worked products. The specification and associated conformance tests enable adopters to correctly implement the specification. Adopter programs enable those implementers to submit their conformance test results for working group approval. Tools, developer samples, educational materials, and sample implementations are often released into open source for industry feedback and participation. So that was a very quick high-level Khronos overview. These slides and much more information are available on the Khronos website. Khronos is committed to play a vital role by providing a safe space for companies to cooperate to create open standards that benefit their own business and the wider industry. Joining Khronos provides significant benefits to all its members, such as industry networking and getting early insights into industry trends and the chance to influence those trends. Early access to draft specifications enables you to bring your products faster to market. If your own company is using Khronos standards and would like a voice and a vote in how these standardization activities evolve, or you wish to use or implement any Khronos standard on your device or platform, Khronos warmly welcomes any company that wishes to participate. We look forward to working with you. Thank you. I'm going to spend a few minutes giving you a summary and an update on the OpenCL open standard for parallel programming. OpenCL is used to accelerate applications by running them across heterogeneous processors, multiple processors of diverse types, including CPUs, GPUs, DSPs, and FPGAs. There's increasing industry interest in parallel processing acceleration to combat the end of Moore's law, as processor frequency scaling gives way to parallel programming as an effective way to deliver needed performance. Khronos has multiple standards for parallel computation. SYCL and OpenVX shown here are high-level programming frameworks. SYCL enables parallel programming using standard C++, and OpenVX uses a graph abstraction to express vision and inferencing functionality. SYCL and OpenVX may be accelerated by lower-level APIs from Khronos that include Vulkan for programming GPUs and OpenCL that lets you program almost any type of processor. Both OpenCL and Vulkan can process the shaders and kernel programs in Khronos' SPIR-V, standard intermediate representation, which enables significant language and compiler ecosystem flexibility, as we will see a little later. OpenCL is a runtime and programming framework that includes C and C++ based languages for creating compute-intensive kernels that can be compiled and executed across any available parallel processors in a system. OpenCL provides APIs to discover accelerator devices, compile kernels for selected devices, execute those kernels with explicit control over kernel placement, memory allocation, and synchronization, and finally gather the results. When deciding between OpenCL or GPU APIs such as Vulkan, many developers that don't need graphics rendering find that OpenCL provides a simpler programming model, a lighter weight runtime, and more rigorously defined numerical precision that can be critical for many compute applications. OpenCL is the most pervasive cross-vendor open standard for low-level parallel programming. OpenCL is deployed by GPU, DSP, and FPGA vendors and used by an increasing number of applications, engines, and libraries, as well as acting as a back-end target for languages, compilers, and machine learning stacks that need a portable API to reach into hardware acceleration, including Khronos' own SYCL and OpenVX. In particular, almost all mobile inferencing engines from companies such as ARM, Qualcomm, Intel, VeriSilicon, Synopsys, TI, Xiaomi, and others use OpenCL as an acceleration backend. Another indication of how widely OpenCL is used throughout the industry is that there are now over 12,000 open source projects on GitHub using OpenCL. That's a tripling in the last 4 years. One of the most topical and significant open source projects right now, of course, is Folding at Home, being used to research the coronavirus. Folding at Home uses OpenCL for GPU acceleration in its network of consumer PCs, which is now delivering an amazing 2.4 exaflops faster than the top 500 traditional supercomputers combined. The latest version of OpenCL is OpenCL 3 that was released in September 2020. OpenCL 3 enables hardware vendors to focus their resources on driver functionality that their customers really need by making all functionality beyond OpenCL 1.2 optional through API queries and language macros. OpenCL 3 also removed the OpenCL C++ language from the specification and recommends instead using the C++ for OpenCL open source front-end compiler that generates SPIR-V code. Existing applications can be easily moved to OpenCL 3. OpenCL 1.2 applications require no changes, and OpenCL 2.x applications also require no code changes if all the functionality that they use is known to be present. To ensure future portability, though, to any OpenCL 3 implementation, developers are encouraged to query for any optional functionality that they use. Several new extensions were released alongside OpenCL 3.0, including asynchronous DMA extensions that enable DSP-like embedded processors to transfer data between global and local memories via DMA transactions. This new functionality complements previous one-dimensional operations by supporting complex memory transfers and use of fences for synchronization of multiple asynchronous transactions running in parallel. There is significant interest in the working group in continuing to extend OpenCL functionality for DSPs and other types of embedded processors. Another set of extensions being actively developed is external memory sharing to enable OpenCL to interop with other APIs such as Vulkan by importing handles to memory and semaphore objects, and then using semaphores to wait and signal the other runtime to coordinate use of the shared memory. Interop between OpenCL and Vulkan will be widely used on both mobile and desktop platforms and will be extended to other desktop APIs in the future, such as DirectX 12 for Windows 10. As an example of OpenCL's growing usage in the mobile industry, Google recently announced a port of TensorFlow Lite to OpenCL to complement its existing OpenGL ES backend. The OpenCL port delivers twice the accelerated inferencing performance on the same devices and over 4 times the performance of unaccelerated inferencing. Even though not officially exposed as part of the Android platform, OpenCL is often provided by mobile GPU vendors, and it is increasingly being used as an acceleration target for mobile inferencing frameworks as well as video and imaging libraries. OpenCL is also used as a back-end target for many machine learning compilers to harness inferencing acceleration. Many companies are researching and developing machine learning compilation stacks. For example, Amazon with TVM, Facebook with Glow, and Google with XLA. All these compiler stacks follow a similar pattern. Firstly, import a trained network, then apply graph-level optimizations to that network, and then decompose the network into executable instructions. All these machine learning compilers can emit OpenCL code to portably access parallel hardware acceleration, illustrating how OpenCL is the most pervasive, close-to-metal execution layer for machine learning libraries, engines, and compilers. As GPU and parallel acceleration solutions become increasingly dependent on this type of compiler technology, SPIR-V is becoming an ever more important part of the Khronos standards ecosystem. SPIR-V is an intermediate language representation that includes heterogeneous parallel processing and graphics operations that can be broken down into instructions for GPUs and other processors. SPIR-V is the only language directly ingested by Vulkan, and it can be imported into a growing number of OpenCL implementations. SPIR-V enables the hardware and compiler communities to innovate independently, as front-end compilers can simply generate SPIR-V code to be ingested and executed by a wide range of runtime APIs. In addition, API runtimes that ingest SPIR-V eliminate the need for front-end compilers to be deployed in embedded systems. Next, I want to talk about the growing industry trend of layering APIs over other APIs through the cross-compilation of shading languages by this increasingly robust open source compiler ecosystem leveraging SPIR-V. For developers, a layered API can enable their application to run on platforms that don't support that API natively. For example, the Google CLSPV compiler enables OpenCL kernels to be compiled and executed on a Vulkan runtime, which, together with the CLVK runtime API translator, enables OpenCL applications to run over Vulkan. CLSPV is already being used to ship demanding OpenCL applications on Android, such as Adobe's Rush video editor that has over 200,000 lines of OpenCL-C running on Vulkan with full GPU acceleration. Layered APIs can also be invaluable to platform vendors as well as developers to enable content on a platform without incurring the support load of an additional kernel-level driver. For example, Microsoft is working on the newly announced OpenCL on 12 open source project to layer OpenCL over Microsoft's own DX12 API. OpenCL on 12 leverages the Mazer open source graphics framework, and Microsoft is working together with Collabora to enable OpenCL wherever Windows 10 ships, including on ARM-based PCs and in the cloud. So that's a overview of OpenCL 3.0 in a nutshell. I hope you found this to be a useful overview. We have put some links here to OpenCL resources, and all of these slides and more are available on the Khronos website. For example, the working group has placed the specifications and conformance tests in open source on GitHub to enable bug fixes and suggestions from the community. And any feedback is also welcome on the Khronos forums. Thank you for your time. I'm going to give you a summary and an update on glTF, which is not an API, but it is instead an open standard file format designed for the efficient and reliable transmission of 3D assets to applications and engines wherever they are needed. The genesis of glTF at Khronos was the realization that all the major media types, images, audio, video, all had formats designed for efficient and compact distribution, apart from 3D graphics. And those efficient transmission formats had created significant market opportunities, and that 3D was really missing out. So Khronos designed the glTF 3D asset format to be focused on being compact and easy to process, so it could become widely adopted. And so we call glTF the JPEG of 3D, as it is the last mile JPEG equivalent that lets you easily transport and deploy and use your 3D assets wherever you need, including in this PowerPoint presentation. glTF is flexible. It can describe any 3D model from single objects to full scenes with animation. It is a pure asset format that can be used in any runtime or application. glTF is also extensible, enabling it to efficiently evolve to meet new use cases. glTF 1 was designed to be used directly in WebGL, and so used GLSL shaders to define materials. WebGL 2 significantly broadened the adoption of glTF by defining physically based rendering, or PBR, materials that are both visually compelling and can be processed by any 3D graphics API on any system. glTF uses JSON to describe the 3D scene hierarchy and uses binary payloads to describe geometry, animations, and skins. Textures are included as JPEG, PNG, or KTX files. glTF also uses textures to define its PBR, or physically based rendered materials, using textures to map how metallic or rough the materials are, or how specular and glossy. This results in very realistic looking objects that can still be rendered very efficiently even on mobile devices and even in a PowerPoint presentation, as we are seeing here. Support for glTF is now widespread throughout the industry as companies realize the efficiency and cost savings of having tools, apps, and engines that can all communicate assets easily to each other. The companies shown here have all implemented glTF support, both in tools that generate glTF assets and engines and applications that ingest those glTF models. If your company supports glTF and your logo isn't here, please do let us know. We would love to add it on. gLTF is an extensible standard to enable it to evolve to meet industry needs, and one of the most widespread developer needs, of course, is for small, compact asset file sizes. The Draco Mesh compression extension uses compression technology developed by Google to enable geometry in a gLTF file to be compressed, typically by a factor of 10 to 25 times. Generating and importing Draco compressed gLTF assets is now widely supported by the major 3D tools and engines with encoders and decoders in open source. But of course, for the smallest asset file sizes, we need compressed textures as well as compressed geometry. And unfortunately, the GPU-accelerated texture landscape is highly fragmented, which can make it tricky for developers with portable applications to know what texture formats to pack into their gLTF assets. Today, developers often need to send multiple copies of textures, which increases file sizes, or send textures in image formats such as JPEG that are small in size but take significant processing and memory to convert to accelerated compressed texture formats that are understood by GPUs. The good news is that Khronos is very close to finalizing the definition of gLTF universal textures. They use basis universal compression technology from a company called Binomial to define super compressed formats that enable small file sizes for transmission and can be efficiently transcoded into the preferred accelerated texture format on the destination device. So for the first time, a gLTF file will be able to include a single optimized set of textures that can be easily unpacked into high-quality GPU-accelerated textures for any device. Universal textures use version 2.0 of Khronos' KTX texture container format to hold the basis universal super compressed textures with precisely defined access to all aspects of the textures, including bitmap levels. And providing portable access to bitmap levels enables applications to implement things like level of detail streaming for textures from any source, for example, by transmitting the smaller bitmap levels first for faster download responsiveness. An important property of universal textures is that they are transcoded on the fly into GPU-accelerated texture formats, so textures never need to be stored as fully decompressed intermediate images on the GPU, as you would need to do when unpacking and re-encoding JPEG or PNGs, and this saves a significant amount of GPU memory. This means that universal textures really give you the best of all worlds: smaller than JPEG assets for transmission, easy transcoding directly into a wide range of GPU texture formats with no intermediate file size image buffer. Another very active area on the gLTF roadmap is a new generation of PBR extensions that add additional material parameters to gLTF's existing PBR definitions, with the first three being clear coat, transmission for transparent materials, and sheen, and those three are already released. These extensions are being designed by a pretty amazing group of industry experts from Khronos member companies who are guiding the gLTF standard to an optimal sweet spot between materials with very high visual realism, but also can be widespread deployed, even on mobile devices. Beyond these first three extensions, the gLTF working group has received requests to support an even wider range of PBR parameters listed here. We will be working on these during the first half of 2021, and so if you have any input or feature requests, please go to the gLTF GitHub where these extensions are being openly discussed. We would love to get your input. And even though the first wave of new generation gLTF PBR materials have just been released, there is already wide industry support, including tools to author the PBR materials and a widening selection of viewers, engines, and applications that can display these highly realistic models, including Khronos' own open source sample viewer. Khronos has also upgraded its open source gLTF validator to check for valid PBR materials and has released a set of samples using the latest PBR materials on GitHub. So that's a very high-level overview of glTF. I hope you found it useful, and I hope you're inspired to try out glTF for your next 3D project if you haven't already. We have put some links to glTF resources here, and all of these slides and more are on the Khronos website. Thank you for your time.
ニールありがとうございます。クロノス概要と OpenCL、gLTF について皆さんご理解いただけましたでしょうか。では続いてなんですけれども、ニールが最後に紹介した gLTF に関連して 3D コマースワーキンググループというのが存在しています。でこのワーキンググループに関してはですね、シュレニックの方が議長を務めているんですけれども、その 3D ワーキンググループ、3D コマースのワーキンググループに関して、シュレニックの方からご紹介させていただきます。それではシュレニックお願いします。
Hi, everyone. Welcome. Thanks for taking the time and thanks for joining us today. My name is Shrenik Sabagi, and I'm the chair of the 3D Commerce Working Group. In my day job, I work for Wayfair, where I lead a small team that is trying to figure out the future of retail and home by investigating emerging technologies. But today, I'd like to talk to you about 3D commerce, why we are here, why we created the group, and what our goals are. When you think of merchandising and the way it's evolved, we've gone from text descriptions of products to images that represent products to now 3D. I believe 3D is a medium that is very impactful for merchandising, especially when you think about the visual computing technologies such as augmented reality and virtual reality, where you can let customers place products in their space or immerse them in virtual environments and have them engage with your product and your brand in a more meaningful way. But before we can see widespread adoption of 3D in retail, there are a few hurdles that we need to overcome. And let me try to illustrate this with some examples. So let's take search as a use case. Google just announced support for 3D and AR search. Now, what that means is you could search for a product and actually see it, engage with it in 3D and place it in your space and then purchase it. And there are many experiences like this where 3D is becoming a lot more powerful in the discovery process. So imagine this across multiple platforms now. Because of the inherent rendering capabilities and the differences in the underlying platforms, to an end user, this chair is going to look a little different across different platforms. Visually, it is not going to be consistent. There are going to be small, slight differences. That leads to a poor customer experience, where the customer does not know which specific platform is the best one to use in order to perceive the product correctly. So that's one problem, and that's on the end user side of the spectrum. But where does this content come from? How do you produce this asset in the first place? What are the problems in that part of the world? So as an example, a manufacturer who wants to sell a product relies on either a retailer or a shopping platform to actually help them sell the product. The retailer or the shopping platform usually employs a team of content creators or employs a service of content creation, where a team of 3D artists then use 3D tools to actually produce the 3D content. So you can see that there are multiple actors and multiple roles that people are playing in multiple organizations to actually produce content. So when you zoom out a little bit and take a holistic view of the entire supply chain and this pipeline of how a product gets created and how it's finally displayed or experienced on a device, multiple people have different definitions of what a virtual product is. And we need to, the problem with that is that as content exchanges hands, that definition changes. And people need to create or recreate assets based on different definitions. this workflow would be a lot more streamlined if we all aligned and actually agreed on what a virtual product is, what constitutes a virtual product, and what defines a virtual product. And that's one of the reasons why 3D Commerce was created. Our mission is to create specifications and guidelines to help with this asset workflow, all the way from product design and manufacturing to the end customer experience. In a simpler way, we want people to be able to create virtual products once in an easy way and have them be able to reuse it across different platforms without having to worry about how that product would look, how people would experience that product. A content creator should have confidence in what they're creating. Will that product withstand time, and will it withstand multiple platforms? Does it have the longevity to do that? That's what we are trying to do. That's the mission. So trying to break that down into the sub-problems, the first one that we're trying to tackle is achieving that visual consistency across platforms. A virtual product should look the same when you see it across different platforms. That's critical to provide a good, consistent end user experience. When you think of products come in multiple shapes, sizes, and colors. But how do you package all that stuff up? How do you do that intelligently so that you can, the content creator can actually do it in an easy way, in a very well-defined way that works well across multiple platforms and can get distributed over the internet and over the wire to the end user devices. Currently, there's no way of doing that. So we plan to create one. And that's one of the goals of 3D Commerce as well. When you think of information about the product, where does that information lie? Should that be embedded inside the product, inside the 3D model, or should that be separate? What kind of information should be embedded in the 3D model? So we're trying to figure out answers to these questions. Metadata, like description of products, the names of the products, something as simple as that. Something more semantic, like where does the product attach to the physical world? What I mean by that is, how does a product interact with the physical world? So for example, a couch, does it sit on the floor? Does a chandelier hang from a ceiling? Does a wall sconce hang from a wall? Things like that, where we're trying to figure out how do we embed that kind of information into the 3D model itself. And last of all, how does someone produce this content in the first place? How do we educate everyone to ensure that people are creating content in a streamlined way that's not wasteful and that's a lot more efficient? In fact, we have released the first version of a set of asset creation guidelines that would help content creators create an efficient asset that would work on multiple platforms. So here's a set of problems that we're trying to tackle as in the short term. And as the group evolves and as we tackle some of these problems, we will take on a different set of problems. And that's where we need your help. We want you to be involved in this effort, especially if you're in the 3D commerce ecosystem, if you're a content creator, if you're a developer, if you're a DCC tool provider, if you are a manufacturer, a retailer, a technology platform, if you're involved in anything to do with retail and 3D technologies, you should be involved. So check out the website, go to khronos.org/3dcommerce. Send us an email, 3dcommerce-feedback@khronos.org to be involved. And definitely check out the first version of our real-time asset creation guidelines. There is a QR code on the screen here. Please try to follow the link and give it a read and let us know what you think. It's a living document that we've hosted on GitHub, and we expect, we would love your feedback on it. We believe that with your help, we can refine the document to a point where it can be broadly distributed and be followed and lead to more streamlined and efficient asset creation. Our goal that you see on the right here is render everything everywhere. I'll end with that. Thank you so much for your time.
シュレニックありがとうございます。皆さん、3D コマースのワーキンググループについていかがでしたでしょうか。gITF というファイルフォーマットだけでなく、それを表示するための仕組みの WebGL であったり、さまざまな部分に関しての取り組み、そしてよりリアルなものを表現するため、どんなデバイスでも表現するために必要な規格の制定に関してご理解いただけたかと思います。では続いてなんですけれども、トム・オルソンからバルカンについて概要を伝えてもらいます。トムなんですけれども、最初から、企業に属していたという形ではなくてですね、研究職、大学の方で、教授をしていたという肩書きを持っている、ちょっと変わったメンバーなんですけれども、バルカンに関しては、その設立当時から、でその前身である OpenJLS のワーキンググループに関しては、ずっと長年にわたって貢献してきてくれています。それでは、トムの方からバルカンについて紹介してもらいます。トム、よろしくお願いします。
Hello, my name is Tom Olson. I work for ARM, and I'm chair of the Vulkan working group. I'm here to tell you about what's been happening in Vulkan over the past year. But before I do that, I want to say a word or two about what Vulkan is. Briefly, Vulkan is a modern cross-platform API for high-performance graphics and compute using GPUs. It gets its hardware model from OpenCL and OpenGLES, and its architecture and design philosophy from AMD's Mantle. What does that mean? Well, a traditional API like OpenGL presents you with a very high-level abstraction that does not look very much like the underlying GPU. To make that work, you have to have a large, complex software driver to do things like memory management, synchronization, error checking, high-level shading language compilation, and so on. It's convenient for the application, but there are problems. The driver uses a lot of CPU cycles. It's hard to understand and it's hard to optimize for. And because the driver doesn't know what the application is trying to do, it is often unable to make good decisions about how to do it. In Vulkan, on the other hand, you get a very thin abstraction, which looks very much like the underlying hardware. Most of the complicated functionality moves out of the driver. Shading language compilation moves offline. Error checking moves into separate optional validation layers, which you use only at development time. And memory management and synchronization move into the application. That's more work for the application, but because the application knows what it's trying to do, it can often do a better job than the driver could. And because the driver is simple, it's easy for the application programmer to predict how the driver will behave. Vulkan has been shipping since 2016. It's available now on a wide variety of desktop OSs, platforms, consoles, etc. There's a lot of great AAA content shipping on it. In mobile, Vulkan is available on essentially all high-end premium Android devices, and there's great content shipping there as well. So that's what Vulkan is. Now I'll talk about new functionalities since last year. Only the highlights. There's more than I can talk about today. So we released Vulkan 1.2 in January. As usual, we created Vulkan 1.2 by bundling together a number of extensions created earlier. And since that functionality is really more than a year old now, I won't say much about it. I do want to point out that a lot of effort went into making Vulkan 1.2 work really well with HLSL as a first-class shading language. A lot of developers told us that they prefer to write their shaders in HLSL, and we heard them and responded. You can, of course, still use GLSL as you always could. There's lots of other good technology in Vulkan 1.2, and it gives us a good foundation for the future, but I don't really have time to talk about it today. Thank you for your time and attention and for the work that you do. I look forward to seeing the amazing things that you are going to do with Vulkan.
トムからの、バルカンの概要についていかがでしたでしょうか。バルカンがどんなものなのかというのの概要については、その OpenGL との違いに関してご理解いただけたんではないかなと思います。で、バルカンの中になんですけれども、実はいくつかのサブワーキンググループが存在しています。その一つ、バルカンのレイトレーシングのワーキンググループの議長を務めているダニエル・コフの方から、概要を説明してもらいます。ダニエルなんですけれども、NVIDIA に勤めてまして、OpenGL ES、OpenGL のグラフィックスドライバーですね。あとは、クロノスのバルカンのレイトレーシングの議長も務めているんですけれども、バルカンとバルカンのセーフティクリティカル、そしてスフィアのワーキンググループに関しては NVIDIA の代表も務めています。13年にわたってそれらの分野に貢献してきているダニエルから、ではバルカンのレイトレーシングについてご紹介します。では、ダニエル、よろしくお願いします。
Well, speaking of doing amazing things with Vulkan, I'm here to talk to you about ray tracing in Vulkan. Hi, everyone. I am Daniel Koch, and I work on graphics drivers at NVIDIA and am the chair of the Vulkan ray tracing subgroup at Khronos. The Vulkan ray tracing subgroup was formed in early 2018 and was tasked with bringing a ray tracing solution to Vulkan. In March 2020, the provisional ray tracing extensions were released to gather public feedback and input into the final design of these extensions. In November 2020, the final Vulkan ray tracing extensions were released, and shortly after that, in December, the Vulkan 1.2.162 SDK was released, incorporating support for these extensions and enabling developers to easily integrate Vulkan ray tracing into their applications. The ray tracing subgroup received a number of design contributions from hardware vendors and examined requirements from both software and hardware vendors. Real-time techniques for ray tracing are still being actively researched, and so the first version of Vulkan ray tracing has been designed to provide a framework while setting an extensible stage for future developments. One overarching design goal was to provide a single coherent cross-platform and multi-vendor framework for ray tracing acceleration that could easily be used together with existing Vulkan API functionality. Software vendors were also clear. We needed to enable content design for contemporary proprietary APIs such as NVIDIA's Optics or Microsoft's DirectX ray tracing to be easily portable to Vulkan. As such, we used a familiar overall architecture, including enabling the reuse of HLSL shaders, while also introducing new functionality and implementation flexibility. We've enabled selected parts of the framework to be optional for deployment flexibility in keeping with the Vulkan philosophy. For this first version, we are primarily aiming to expose the full functionality of modern desktop hardware, but in a way that is hardware agnostic and can be accelerated via existing GPU compute or dedicated ray tracing cores. So how do you use Vulkan ray tracing? Like many other ray tracing APIs, the first step is to build the scene geometry into an efficient two-level acceleration structure so that searching for ray tracing intersections can be optimized. The precise internal organization of the Vulkan acceleration structure is opaque to the application so that the hardware vendor can optimize it to match their own architecture. The KHR acceleration structure extension provides the ability to create and build acceleration structures on the GPU or optionally on the host. More about that later. It also provides acceleration structure management commands, which enable compaction and serialization of acceleration structures. An acceleration structure is a highly optimized implementation-dependent data structure that is built from the application-provided scene data and placed in a buffer. This opaque data structure is used to achieve high-performance ray intersections in complex scenes. The acceleration structure is divided into a two-level hierarchy, as shown. The bottom-level acceleration structure contains triangles or axis-aligned bounding boxes of custom geometry that make up the scene. Since each bottom-level acceleration structure may correspond with what would be multiple draw calls in the rasterization pipeline, each bottom-level acceleration structure can contain multiple sets of geometry of a given type. The top-level acceleration structure contains references to a set of bottom-level acceleration structures. Each reference includes shading, transform information for that reference. The bottom-level acceleration structure is only used by reference from the top-level acceleration structure. The top-level acceleration structure is accessed from the shader as a descriptor binding or by device address. Next, we need to launch rays into the scene to determine how those rays intersect and interact with scene geometry, materials, and light sources, and to process those intersections with programmable flexibility to enable a wide variety of visual effects. Vulkan provides two ways to traverse the scene. The first method, shown on the bottom left, uses the new ray tracing pipeline that enables the application to compile a set of shaders into a pipeline to handle any desired ray and material processing, and then launch a grid of rays into the scene with the ray tracing pipeline invoking the appropriate shader when intersection occurs, or a miss shader if no hits occurred for that ray. The second technique to fire rays, called ray queries on the bottom right, is much more explicit and enables any type of shader to launch a ray at any time and process the intersection data however it wishes. This is a very flexible technique, as the shader also controls how the traversal proceeds through the scene, but it does place more burden on the shader author. The KHR ray tracing pipeline extension adds the new ray tracing shader stages, pipelines, and associated commands. The corresponding SPIR-V KHR ray tracing and GLSL-X ray tracing extensions define the associated SPIR-V and GLSL constructs. Ray tracing pipeline work is launched using VK command trace rays KHR. This command invokes an application-defined set of ray generation threads, which can call trace rays X from the shader, starting traversal work on the specified acceleration structure. During traversal, if required by the trace and acceleration structure, application shader code in intersection and any hit shaders can control how traversal proceeds. After traversal completes, either miss or closest hit shader is invoked. The different shaders can communicate parameters and results using ray payload structures between all traversal shaders and hit attribute structures from the traversal control shaders. To enable the traversal phase to know which shader to invoke after a given step of traversal to control or respond to the traversal, the implementation uses a shader binding table. Each shader entry in the table consists of a shader group handle plus an optional shader buffer record, which the application may use for instance-specific data such as buffer device addresses or descriptor indices. The address for any given shader is computed by the traversal through a combination of parameters to the trace rays API call, parameters to the trace rays shader call, and information stored in the acceleration structure. The KHR ray query extension enables ray queries for all shader stages, including graphics, compute, and ray tracing shaders. The corresponding SPIR-V KHR ray query and GLSL-X ray query extensions define the associated SPIR-V and GLSL constructs. Ray queries can be used to perform ray traversal and get a result back in any shader stage. Other than requiring acceleration structures, ray queries are performed using only the new shader instructions. Ray queries are initialized using ray query initialize, which specifies an acceleration structure to traverse and various properties of the ray being traced. Next, ray query proceed is used to start the traversal. After an intersection candidate is found, the shader can examine properties of the potential intersection and of the ray itself using instructions which are accessible to shader during traversal and specify how the ray should be handled, either by generating intersection details, confirming a hit, or terminating the ray. If the traversal is not finished or the ray terminated, ray query proceed can be called again to continue the acceleration structure traversal. A ray tracing application can use hundreds or even thousands of shaders to process the many types of visual effects in a scene. Compiling that many shaders into a ray tracing pipeline can be intensive enough to cause application stuttering when new scenes are loaded or when new scene effects are needed. It can be particularly aggravating to discover that a scene suddenly needs a new shader, and that triggers the entire set of shaders being recompiled and reloaded. To avoid that overhead, the KHR pipeline library extension enables a library of SPIR-V shaders to be incrementally compiled into an existing ray tracing pipeline, saving the need to recompile everything from scratch. A pipeline library is a pipeline which includes the normal state and shaders, along with an additional flag to indicate that is not intended to be bound directly to the API, but is intended to be used as a library that will be linked with a later pipeline. Pipeline libraries can also be included in multiple ray tracing pipelines, allowing shader compilation results to be reused across pipelines. Ray tracing pipeline creation may include both pipeline libraries as well as additional ray tracing shaders directly. All of the compilation state from each pipeline must match to successfully create the final linked program. Pipeline libraries can be helpful when dynamically managing shaders in a scene, but there is still significant setup processing for any ray tracing application, not just compiling shaders, but also loading geometry into acceleration structures. To help applications use all the available processors in a system for scene setup, we have provided the ability for the host CPU to build acceleration structures in host memory for subsequent download to the GPU, enabling the host CPU to perform setup in parallel with the GPU performing other work. The KHR Deferred Host Operations extension provides a mechanism where the driver returns a deferred work handle to the application for later execution, enabling the application to control work execution and to distribute the work onto multiple cores and background threads. In a ray tracing application, deferred host operations can be used to asynchronously leverage multiple CPU cores to build host acceleration structures. They can also be used to parallelize ray tracing shader compilation and pipeline generation. So this was just a quick overview of the Vulkan ray tracing extensions that are now available. Production ray tracing drivers for AMD and NVIDIA GPUs are now shipping, and Intel drivers should be available later this year. For more information about Vulkan ray tracing, here are a number of links to blog posts, tutorials, and other resources. Welcome to the era of portable, cross-vendor, cross-platform ray tracing acceleration. We look forward to seeing how you will use it.
ダニエル、ありがとうございます。バルカンのレイトレーシングに関しての概要いかがでしたでしょうか。ちょっと専門的な部分もあったかと思うんですけれども、開発者の皆さんにとっては非常に有益な情報になったのではないかなと思います。では続いてなんですけれども、同じバルカンではあるんですけれども、グラフィックスというよりは、マシンラーニング、AI の部分に関連して使われているテクノロジーのワーキンググループ、ピエール・ブディエの方から、バルカンのマシンラーニングについて紹介してもらいます。ピエールなんですけれども、17年間にわたってクロノスグループ関連の使用に非常に貢献してくれています。NVIDIA でプリンシパルエンジニアを務めていて、バルカンと OpenCL グラフィックスドライバーの GPU のアーキテクチャに取り組んでいる人間です。では、ピエール、バルカンのマシンラーニングについての紹介お願いします。
Everybody has heard about the cool new things that can be done using machine learning, and I'm here to talk to you about how this can be achieved using Vulkan. Hi everyone, I'm Pierre Boudier. I work on graphics drivers at NVIDIA, and I'm the chair of the Vulkan machine learning subgroup at Khronos. This group was formed in spring 2019 and was tasked with bringing a machine learning solution to Vulkan. The machine learning subgroup received a number of design contributions from hardware vendors and examined requirements from both software and hardware vendors. The design goal was to enable the ecosystem with an easy integration with the rest of the Vulkan API functionality. Machine learning is still an active area of research, and new neural networks are coming out every year. While there are a number of natural building blocks like matrix simplification, convolution, rectified linear unit, sigmoid, hyperbolic tangent, there is a combinatory explosion of architectures, as well as new arithmetic concepts being added every week. For instance, locality-sensitive hashing, sparse matrices, quantized weights, binary weights. So software vendors were also clear. There is a need for a solution in the Vulkan ecosystem which has lower overhead than using interop with some other API, and without having to install large external frameworks like Python. Luckily for us, we did not have to start from scratch, as Vulkan already had a compute API capability built in from day one. Additionally, some of the new functionality, specifically targeting machine learning, has some crossover requirements with traditional graphics compute usage. As a result, new extensions were introduced in the initial release of Vulkan that benefit directly machine learning specific workflows. So what does it mean to do machine learning in Vulkan? In a typical workflow, a data scientist will create a neural network by training it on a desktop or in the cloud using high-end accelerator systems. Those networks are then exported using some exchange format, which includes both the definition of the computational graph and the value of the parameters. Two of the formats are NNEF and ONNX, NNEF being defined and supported by Khronos. At runtime, the application would load those formats and generate some compiled code that can be executed in a step called inferencing. The application would use the Vulkan API via compute shaders to offload the computation on the GPU accelerators. So how does one use compute shaders and what precisions should be used? Machine learning is about running a computational graph, which by default is usually done in 32 bits in the Python frameworks. The precision has to match between training and inferencing. There is actually very little difference between training and inferencing from an execution point of view. Training is just running 2 extra graphs to backward propagate gradients and to update the parameters. For many architectures, it is actually possible to use lower precision than the full 32-bit, which results in both faster execution and reduced data storage. 16-bit floating point can be used by monitoring the magnitude of the gradients during training to avoid 1 to 0 for small values. 8-bit integer can also be used in quantized network, which are generated by distillation phase. Vulkan supports those data natively since the version 1.2 or via the extensions VK-KHR shader float 16 int 8 and VK-KHR 8-bit or 16-bit storage. An upcoming extension, FPV-KHR integer.product, allows to write optimized kernels using integer math without having to rely on compiler optimization. Next, we look into ways to improve Vulkan compute for ML. The first upcoming extension, VK-KHR workgroup memory explicit layout, improved the efficiency of loading data into shader memory without blocking the arithmetic units. The second upcoming extension, VK-EXT-ML primitives, exposes common building blocks that are found in the layer of the popular neural nets, which the driver can then optimize more thoroughly. More details will be shared for those 2 extensions once they become publicly available. The third extension is already available, VK-NV Cooperative metrics, and can be used in a shader to directly access dedicated hardware optimized for matrix multiplication. This is typically done for matmul and convolution layers using 16-bit floating point precision. So how does one get started? An easy way to run your networks in Vulkan is to compile the computational graphs thanks to a generic compiler. We will mention 2 open source projects. TVM, originally started at the University of Washington, will compile networks into SPIR-V that can be run on top of the Vulkan API. MLIR-IRE is a multiple level IR infrastructure developed inside LLVM, associated with an IR execution engine, IRE, which can generate both SPIR-V code and the associated Vulkan API code. Looking into more detail of MLIR RLE, Google has been collaborating closely at Khronos when developing the Vulkan-based inferencing solution. The compiler starts from a generic XLA HLO description of the network, which can be generated from the TensorFlow PyTorch Python frameworks. It will then lower successively into lower level of abstractions, each one of them targeting a domain-specific dialect. The last output is a combination of the SPIV code that can be compiled to specific GPU ISA by the driver, and a list of Vulkan API calls in order to submit those kernels and manage the associated allocations and synchronization points. The compiler has a unified view of the entire computational graph and can optimize efficiently across layers and schedule dispatching of operation without unnecessary synchronization. Other third-party frameworks do provide acceleration using Vulkan. Let's have a look at a few. Alibaba provides the MNN library, which can do both inferencing and training on mobile platforms. It is already being used in many of the most popular Alibaba applications like Taobao, Tmall, Youku, DingTalk. Tencent provides the NCNN library that can do inferencing on multiple platforms, mobile and desktop. It is being used by many of the popular Tencent applications such as WeChat, Baidu, QQ, Qzone. Finally, Axe Inc. provides SDK called ILIA, which has highly optimized implementation of many of the popular networks across multiple platforms and provide multiple support options for companies interested in deploying neural nets. There are options to do machine learning with Vulkan outside of purely running neural nets. VKFST is an open source project started by Yuli, which provides highly efficient fast Fourier transform kernels with lots of possible parameterization. It has shown great results for image resampling, image registration, and even in generic signal processing for physics simulation. Compute is a framework that allows writing kernels and algorithms for deployment on multiple vendor graphics cards with integration in both C++ and Python. Finally, Unity provides ML agents, which can be used to train intelligent agents within the Unity game engine based on reinforcement learning, proximal policy optimization, and soft actor critic. So here's our call to action. This was an overview of the Vulkan machine learning capabilities that are now available. Production drivers have been shipping for a while on many devices. We are welcoming feedback from application or framework developers. If you have needs which are not addressed at all by the existing solutions, or if you have pain points which could be alleviated, do not hesitate to contact us. We are interested in both neural net workflows and other classical machine learning algorithms like random forest, logistic regression, TSNE, k-nearest neighbor. My email address is pboudier@nvidia.com. Alternatively, you could decide to join the Vulkan advisory panel or even become a Khronos member. Thank you.
ピエールありがとうございます。皆さん、バルカンのマシンラーニングについての概要、いかがでしたでしょうか。グラフィックスという部分に関してなんですけれども、最近自動運転などで AI で画像処理であったりというものを非常に使うことが機会が増えていると思います。そういった部分で利用が増えているというのが皆さんにもお分かりいただけたんではないかなと思います。で、その画像処理の部分、ビジョンの処理についてですね、実際に事例ということで AX 株式会社様の方から、バルカンのマシンラーニングに関してご紹介していただきます。それではよろしくお願いいたします。
それでは、バルカンを活用した高速 AI フレームワーク実装 IDEA-SDK での事例と題しまして、AX 株式会社が発表させていただきます。AX 株式会社は2019年5月に創業した会社で、AI を実用化する会社として位置づけています。AI と GPU の専門家が多数在籍している会社となります。メインとなるプロダクトは、GPU を使用して高速に AI 推論を行う AI フレームワークである IDEA-SDK の開発と販売です。ポリケスで記述された AI モデルを読み込んで、バルカンを使用した高速推論を実現します。また、100種類以上の学習済みモデルを提供しており、AI 機能を学習なしでお客様のアプリに簡単に組み込みは可能です。もちろん、お客様で学習したモデルを読み込むことも可能です。IDEA-SDK は推論に特化した AI フレームワークです。 特に高速処理、クロスプラットフォーム対応、マルチランゲージ対応、最適化された開発 UX に特徴があります。高速処理ではバルカンとコンピュートシェーダーを使用した最適化や、レイヤーフュージョンなどによるグラフ最適化を行っています。クロスプラットフォーム対応では OS やデバイスを選ばない推論を実現しています。マルチランゲージ対応ではプログラミング言語を選ばない推論を実現しています。最適化された開発 UX として、すべてのプラットフォームで統一された API、同一の AI モデルの動作保証を行っています。また、完全自社開発を生かして API の長期供給を行っています。IDSDK の採用事例です。株式会社セルス様のクリップスタジオペイントにご採用いただいておりまして、実際に Android 端末上でバルカンを使用した高速推論をご利用いただいております。また、株式会社ユニットコム様の AI 開発、ディープラーニング専用 PC にデモアプリを同行させていただいています。こちらが IDSDK のアーキテクチャとなります。アイデアモデルスが提供するモデルファイルやお客様のモデルファイルを IDSDK が読み込み、ランタイムでグラフ最適化を行います。グラフ内の各レイヤーはコンピュートシェーダーで実装したバルカンのバックエンドで実装することで高速処理を行います。我々の強みはこのバックエンドとシェーダーコードを独自実装している点にあり、クロスプラットフォームとポータビリティを実現しています。IDSDK がバルカンを使用するモチベーションについて説明します。まず GPU を選ばずに動作させたいということです。世の中には多くのベンダーの GPU が存在するため、その全てに対応することは大変です。バルカンを使用することでデスクトップとモバイルを選ばず、どのベンダーの GPU でも実行可能としています。また、OS に関しても、バルカンを使用することで、Windows、Android、Linux のすべてで一貫した動作を実現しています。また、重要なのがユーザー関係の特殊なソフトウェアをインストールせずに GPU を使いたいということです。バルカンはゲームで広く使用されており、標準ドライバーのみで実行可能なため、アプリケーションに同梱して再配布することが容易です。アプリケーションに同梱して再配布するという観点で、ライブラリサイズも重要でして、バルカンを使用することで 2.8MB 程度のライブラリサイズで AI 推論を実現しています。こちらがですね、実際に IDSDK とバルカンを使用して AI の高速推論を行うデモとなっております。デモアプリは Unity で開発しておりまして、クロスプラットフォームで動作します。IDSDK はモデルファイルを読み込み、動画やカメラ、画像に対して画像認識を行っています。現在は映っている画面はですね、ヨロブイスによる物体の検出になっておりまして、このデモでは様々なモデルをですね、実際にバルカン上で動かすことが可能です。例えば、顔の認識、顔の位置であるとか、顔から表情を検出するというところでしたり、入ってきた画像に対してどこが、道路か、どこが人か、どこが車かっていうのをセグメンテーションするモデルも動作します。また、髪の毛の領域をセグメンテーションするモデルとかですね、あと、このように群衆計測、入ってきた映像からここに何人ぐらい人がいるかっていうのを表示するモデルですとか、あと一般的によくベンチマークで使われるレズネット50物体識別のモデルとかですね、あとは骨格検出のモデルですね、というのももちろん動作します。このように当社はですね、IDSDK とバルカンを使用することで多様なモデルがですね、実際にバルカンを使用して高速に推論できることを実証しております。ここからは少し技術的な詳細になります。IDSDK では、コンボリューションやプーリング、アクティベーションなどの各種のレイヤーの処理を、コンピュートシェーダーを使用して実装しております。AI 処理において最も負荷が高いのはコンボリューションでして、これをいかに高速化するかが重要になります。IDSDK ではコンボリューションを高速化するため、ミノグラッドのアルゴリズムをシェーダー実装しています。ミノグラッドアルゴリズムは、コンボリューションの入出力に変換をかけることで、行列的演算の計算量を減らす手法です。フィルタケースと画像を別の空間に作動し、行列積を行った後、元の空間に戻します。これにより、3×3 コンボリューションにおいて、4個の出力を得るために必要な36回の積和演算が16回まで削減可能です。また、フィルタケースの変換に関しましては、事前に行って、キャッシュしておくことが可能です。行列積の実装におけるブロックサイズは、今回 m=n=k=4 で実装しております。一部、アドレドのみですね、m=8 をした方が高速だったため、m=8 を使用しております。一つのブロック内の行列積は、コンピュートシェーダーで実装しておりまして、ワークグループの同期を行わず、一つのインボケーションで計算しております。 また、メモリアクセスの効率を改善するため、メモリは16バイトにアラインして、ベクフォー型として1命令で読み込んでいます。その後もですね、できるだけベクトルを分解せずに扱うことで、メモリアクセスを最適化しております。これらの最適化によってですね、バルカンで高速なコンボジションの処理というのを実現しております。また、当社の調査の結果ですね、VKQ サブミットのオーバーヘッドも無視できないことを確認しておりまして、ここではサブスレッドを活用しております。具体的にはコマンドバッファーを処理するスレッドを別に立ててですね、AI のレイヤー処理が要求されると、専用スレッドにコマンドバッファーを付与するような仕様となっております。これによって専用スレッドがアイドル時に Q のコマンドバッファーを一斉に VKQ サブミットすることが可能になりまして、VKQ サブミットのオーバーヘッドを削減することが可能となっております。まとめです。バルカンを使用することでですね、デバイスと OS を選ばず、標準ドライバーのみで AI の高速処理を実現しました。また、アイデアモデルスの100種類を超える AI モデルで実際にバルカンによる高速推論を実証しております。アイデア SDK を使用することで、バルカンを使用した高速推論を簡単にアプリケーションに組み込みは可能です。AX 株式会社では、コンサルティングからモデル作成、SDK の提供、あと AI を使用したアプリ、システム開発、サポートまで AI に関するトータルソリューションをご提供しております。ですので、ぜひお気軽にお問い合わせいただければなと思っております。また、当社では技術ブログなども行っておりますので、ぜひご参照ください。また、バルカンを使用した IDEA SDK の無償評価版もダウンロードできるようになっておりますので、ぜひお試しいただければなと思っております。講演は以上となります。ご清聴いただきどうもありがとうございました。
AX の方からのプレゼンテーションいかがでしたでしょうか。ありがとうございます。では続いてなんですけれども、QA のセッションに入らせていただきます。ご質問の方なんですけれども、順番にちょっと読み上げさせていただこうと思います。でもしですね、まだ質問の方を書いていない方がいらっしゃいましたら、Q&A のパネルの方にご記入ください。まず1つ目なんですけれども、最後のAX 様の質問に対する質問なんですけれども、対応しているネットワーク、レイヤーはどうなっているのかという点についてなんですけれども、AX の方、ご回答いただけますでしょうか。
はい、AX の客と申します。よろしくお願いします。今回ですね、IDEA SDK では今現状100種類以上のモデルと100種類以上のレイヤーに対応していまして、ほとんどオニキスモデルが動作するような形になっています。またですね、4次元以上の5次元の点数というのも対応していまして、3D コンボジションなどですね、割と新しいレイヤーにも対応しています。対応モデルの一覧はですね、GitHub に公開していますので、ぜひご参照いただければと考えています。また対応レイヤーの一覧自体はですね、評価版ダウンロードいただきますと、そこのドキュメントに記載していますので、そちらを参照いただければと思います。よろしくお願いします。
ありがとうございます。では続いてなんですけれども、順番に質問が来ていますので、それをニールの方に、回答してもらおうと思います。So, Neil, could you please answer the questions?
Yep, we have one question from Christian in the audience. The question is, are there plans to expose OpenCL as a web API like WebGL? It's an interesting question. Actually, Khronos did create a WebCL standard for OpenCL in the web. It was back in 2011, almost 10 years ago. But in the end, it was too expensive for the browser vendors to add yet another accelerated API into the browser stack. They put an enormous amount of effort into supporting WebGL, and yet another API was just too much for them. So all is not lost, though. The best way to get acceleration, compute acceleration in the browser is to use WebGL compute shaders, GPU, and there are many applications shipping in the browser that does use WebGL for GPU compute. And there's a new generation of 3D API for the web coming, being developed by the W3C called WebGPU, and which is much closer to Vulkan than WebGL is to OpenGL. And WebGPU is going to have fully functional dedicated compute shaders, as well as the normal graphics shaders. So there'll be even more flexible compute acceleration when WebGPU arrives in the next few years. Okay. And I think we probably have time for one more. And there's a question here on glTF. The question is, glTF is meant to be deployable everywhere, but there aren't PBR materials too compute intensive for some platforms such as mobile. So that's another good question. glTF's mission is definitely to be deployable everywhere, usable everywhere, including on mobile devices. And traditionally, PBR materials have been used by high-end ray tracing renderers. So it is interesting to see them come onto mobile devices. But the glTF working group is very interesting. We do have a lot of the industry-leading experts on PBR materials and how to render them. And the working group is using that expertise to really push forward the boundaries of what is possible to define in a PBR material that looks very realistic, but is still processable on a mobile device. And not only is that good for glTF, no, we think it's good for the industry to have these standard PBR materials that not only look awesome, no, but have been designed to run very efficiently on all kinds of devices, including mobile phones. So, all right, perhaps just one more. One more? Yeah, okay, one more. So let's see, we have one here. So most of the Khronos members are engineering companies. So why did 3D Commerce come to Khronos? That's a good question. So I think there's a couple of reasons. The commerce industry wanted to develop 3D standards, and Khronos has a good reputation in the area of 3D graphics. And so we were kind of the natural place to approach for developing the 3D commerce standards. And we have our exploratory group process that Takashi-san was explaining earlier. And that let us explore together whether standards were the right solution and was Khronos the right place to do it. And we are very happy that they decided yes. And now we're in a very good position because we have a very interesting group of people at the 3D Commerce Working Group. It's an excellent mix of engineering companies and retail and commerce companies. So we have a very tight connection between the requirements and the problems we're trying to solve and the necessary engineering expertise to actually create those standard solutions. So there's a lot of good work going on at 3D Commerce. All right, I think that's all the time we have for. So Takashi-san, back to you.
Oh, thank you. まだいくつか質問の方はあるんですけれども、ちょっとお時間の関係で、これで Q&A の方は移らせて終了させていただいて、まとめに入らせていただきたいと思います。AX 株式会社様、ご講演ありがとうございます。クロノスのバルカンのマシンラーニングを使った事例の方いかがでしたでしょうか。それではですね、これ以上で、本日のプレゼンテーションはすべて終了となります。で、最後にですね、私の方から、ご紹介なんですけれども、今日ご紹介したスライドであったり、もしくは、それ以外の標準規格に関する情報に関しては、クロノスのウェブサイトの方からアクセスできるようになっております。で、皆さんですね、今日参加していただいている方、メンバーの方もメンバーでない方もいらっしゃると思うんですけれども、ぜひクロノスグループの方にご参加いただければと思います。クロノスグループに参加していただくメリットなんですけれども、こちらのスライドの右下の方に書いてありますように、例えば業界のトレンドを取り込んだり、もしくはその専門の分野ですね、さまざまな分野のエキスパートとつながれるという点であったり、あとは実際にビジネスをする際にですね、業界の中においてどういった方向性を形作っていくのかという部分に関して影響を与えることができる というのも非常に大きな魅力だと思います。あとは IP の知的財産権を保有する会社様に関しては、それを保護するようなものもすべて含まれております。で、クロノスグループで作成している標準規格を制定していくんですけれども、それがリリースする前に、さまざまな情報にアクセスすることができますので、新しい仕様がリリースされると同時に、それに準拠した新しい製品というものをリリースすることができるようにもなります。あとは、そうですね、クロノスグループに入っているという部分で、業界のリーダーとしての認知というのがマーケットにも広く伝わるのではないかなと思います。はい。では、今回の、この YouTube、今回の動画なんですけれども、YouTube の方からもアクセスできるように公開させていただく予定です。あと、イベントのページの方にも、スライド資料、動画の方をアクセスできるようになる予定になっています。で、何かですね、クロノスグループに関してご質問のある方はですね、ぜひ、私の方まで遠慮なくご問い合わせいただければと思います。本日は本当にお忙しい中ご参加いただきましてありがとうございます。それでは失礼します。